When you launch a $10 billion telescope to deep space, you should be prepared to have some of your long-held theories about the universe challenged. Scientists knew this, but were still surprised by the James Webb Space Telescope's latest discovery. What happened before the Big Bang? What has the JWST discovered about the Big Bang, and how does it affect astronomy as we know it? Stay tuned as we dive into the James Webb Space Telescope's discovery of what happened before the Big Bang. Do you know the Big Bang? Many people do, especially if they're a fan of the popular TV show with the same name. However, the recent findings by the JWST hint at what happened before the Big Bang. But first, what exactly happened during the Big Bang, and how did it bring us here? According to this theory, the universe started as a very hot, dense, and tiny point of matter and energy, which then rapidly expanded and cooled down. This expansion and cooling process created the conditions for the formation of atoms, stars, galaxies, and other structures that we observe today. The Big Bang theory is supported by several lines of evidence, such as Hubble's law. This is the observation that distant galaxies are moving away from us, and the farther they are, the faster they recede. This implies that the universe is expanding and that it was smaller and denser in the past. The rate of expansion can be used to estimate the age of the universe, which is currently about 13.8 billion years. Cosmic microwave background radiation, CMB. This is the faint glow of radiation that fills the entire sky, which is a remnant of the intense heat and light that filled the early universe. The CMB has a very uniform temperature of about 2.7 Kelvin, with tiny fluctuations that reveal the density variations in the primordial plasma. The CMB also shows that the universe was opaque to light until about 380,000 years after the Big Bang, when atoms formed and allowed light to travel freely. Abundance of primordial elements. This is the observation that the universe is mostly made of hydrogen and helium, with traces of other light elements like lithium, beryllium, and boron. These elements were produced by nuclear fusion reactions in the first few minutes after the Big Bang, when the temperature and density were high enough for nuclei to form. The relative amounts of these elements agree with the predictions of Big Bang nucleosynthesis, a theory that describes how matter was created in the early universe. Galactic evolution and distribution. This is the observation that galaxies have different shapes, sizes, ages, and compositions depending on their location and history. Galaxies are not randomly distributed in space, but form clusters and superclusters that are connected by filaments of matter. These structures reflect how matter has clumped together under gravity over time, forming stars and galaxies from smaller fluctuations in density. The oldest galaxies are found near the edge of our observable universe, while younger ones are closer to us. But what really happened before the Big Bang? One of the most exciting and difficult problems in cosmology is what happened before the Big Bang. The Big Bang theory outlines how the universe originated in an extremely dense and hot state, then expanded and cooled over time. It does not, however, explain what produced or preceded this initial state, or whether such a question is even relevant. There are various plausible explanations that scientists have proposed for what happened before the Big Bang. Among them are the Big Bounce. This theory holds that our universe is part of a cyclical process in which a prior universe collapsed into a singularity and then bounced back into a new one. This cycle may have been repeated an endless number of times. The Big Bounce could be caused by quantum processes, gravity, or other spatial dimensions. The ekpyrotic scenario, which proposes that our universe arose from the collision of two branes, which are tiny sheets of matter and energy that reside in a higher dimensional region. The collision sparked a burst of inflation, a rapid expansion that smoothed out our universe's initial circumstances. The branes could clash on a regular basis, resulting in the creation of numerous universes. The pre-Big Bang scenario. This is the theory that our universe developed from a condition of low energy and high curvature into a state of high energy and low curvature. This transition included a period of superinflation, which magnified quantum fluctuations and transformed them into seeds for cosmic structures. The pre-Big Bang scenario is based on string theory, which is a framework that unites all natural forces and particles. The no-boundary proposal. This is the theory that our universe has no boundaries in space or time and that the Big Bang is a smooth zone when the universe's size becomes very small. The no-boundary proposal describes the beginning of the cosmos as a quantum fluctuation from nothingness using quantum physics. A wave function that encodes all potential histories determines the structure and attributes of the universe. And it's important to note that these possibilities are not mutually exclusive and they may be compatible or complementary in some cases. Now, finding out how the universe grew up is one of the biggest science goals of the JWST. And with its latest discovery, it's found the earliest proto-galaxy cluster ever discovered, just 650 million years after the Big Bang. In theory, the universe has a hierarchy of how things develop. The universe was almost completely uniform in the early phases of the hot Big Bang. All matter and energy were dispersed uniformly throughout space, with small 1 part in 30,000 perturbations overlaid above that uniform background. These oscillations are caused by cosmic inflation, which preceded and established the Big Bang, and they exist on all cosmic scales, tiny, intermediate, and huge. But because matter and radiation interact and the universe expands, these smallest scale fluctuations are washed out. The intermediate scales have peaks and valleys in whether density fluctuations are enhanced or suppressed, and the largest cosmic scales are unaffected. This information is contained in the Big Bang's residual glow, the cosmic microwave background, where it may still be seen today. The overdense regions then begin to gravitationally develop, while the underdense portions give up their matter and energy to their denser surroundings. Despite the fact that gravitation is an infinite range force, gravitational growth does not occur evenly throughout the universe. The important thing to understand is that gravity, like other messages in the universe, does not reach everywhere instantly, but is instead restricted by the speed of light. If you have an overdense region in space, it can attract matter that is nearby in a certain amount of time, but matter that is 10 times as distant will take at least 10 times as long, probably more, given that the universe is expanding to feel the gravitational attraction from the same object. The longer it takes for gravitational pull to begin, the larger and grander the cosmic scale, from star clusters to galaxies to groups and clusters of galaxies and beyond. And then once a large-scale region experiences gravitational attraction, several events must occur before a bound structure forms, all of which take time. As it moves away from the gravitational overdensity's center, the receding matter must slow down. To cause gravitational collapse, the overdense zone must reach a critical mass, roughly 68% more than the average density. The large-scale structure must then stop declining, reverse orientation, and begin collapsing. And then, finally, we'll have a bound object, subcomponents that are all part of a larger bound large-scale structure. On a smaller scale, molecular clouds of gas, dust, atoms, and dark matter are the first formations to collapse, giving rise to the first stars and star clusters. And while the most common of these overdense regions may take 200 to 250 million years to collapse, the earliest ones to do so, that is, those with the greatest initial overdense conditions, may be able to do so in as little as 50 to 100 million years. Now, as stars form, they emit radiation and winds, which creates incomprehensibly complex environments, making it difficult to predict any details about these early structures. As these early clumps of matter draw more matter into them, they also find and merge with one another, forming the universe's first massive galaxies. We've detected richly evolved galaxies as early as 320 million years after the Big Bang and the limits of what JWST has observed so far, with many of these early ones being huge, rich in heavy elements, and teeming with continuing star formation. JWST was fully expected to discover these objects, and there is still reason to believe that JWST's capabilities will disclose populations of totally immaculate stars as well as even earlier galaxies. On the broader cosmic scale, however, this messy physics plays little to no role. On the size of individual galaxies, however, one must contend with continuous star production, huge star winds and radiation, stellar deaths and cataclysms, cooling and infall of gas and other atom-based matter, mergers and accretion, ionization, and the interaction of dark matter with normal matter. But when it comes to the creation of galaxy clusters, these causes play a very tiny impact. Instead, the formation of galactic groups and galaxy clusters is largely determined by three well-known factors. The universe's expansion is fully determined at all cosmic times once we know what's actually in the universe. The magnitude of the initial overdensity on the relevant cosmic scale, which allows us to compute any such object's rate of gravitational growth, and how that gravitational increase progresses over time, taking into account the relevant interplay of multiple cosmic scales. All of that messed up stuff that happens inside a galaxy, sometimes derisively referred to as gastrophysics, has no effect on the creation and growth of galaxy clusters. Only gravity matters. Now, prior to JWST, there were a variety of methods for exposing these galaxy clusters throughout cosmic history. The simplest and most straightforward method was to identify large numbers of galaxies that existed in the same field of view at identical redshift distances to one another but with a significant velocity dispersion. Galaxies within the cluster moved at speeds of several hundred or even a few thousand kilometers per second relative to one another. This method made it simple to discover nearby galaxy clusters like Coma and Virgo. Galaxy clusters that are heated, such as by the collision of fast-moving gas clouds or by intensive star formation processes, release X-rays throughout the intergalactic medium within the cluster, leaving an identifying signal if we probe them with the appropriate wavelengths of light. These X-ray producing clusters are useful not only for identifying clusters, but also for learning about their masses, gas contents, and merger histories. And finally, galaxy clusters have been revealed by the collective effects of their gravity, the phenomenon of strong and weak gravitational lensing. A massive galaxy cluster will be distinguishable from a set of unclustered galaxies because of the lensing features caused by intracluster matter, the mass within the cluster that exists between the individual galaxies. CL-J1001 plus 0220, identified through its X-ray emissions and whose light we see 2.7 billion years after the Big Bang, is a relatively nearby mature galaxy cluster. It contains 17 distinct galaxies, more than half of which are starburst galaxies, forming stars in a massive burst that spans the entire galaxy. Galaxy clusters, on the other hand, do not begin as mature objects, but rather evolve from an unformed condition through a protocluster phase. To identify the first such objects, we must seek protoclusters of galaxies, groups that haven't yet heated up their gas enough to emit X-rays. A survey using the premier ground-based observatories such as Subaru, Keck, and Gemini revealed two very distant collections of several galaxies in the very early universe. One consisting of 44 galaxies at a redshift of 5.7, corresponding to an age of 1 billion years after the Big Bang, and another consisting of 12 galaxies at a redshift of 6.6, corresponding to an age of 800 million years after the Big Bang. These protoclusters were the first examples of groups of galaxies in a comparable location in space, with their speeds and masses showing that they are definitely in the process of becoming gravitationally linked and may have already crossed that threshold. Scientists fully expected to break this cosmic record with JWST's unparalleled cosmic vision, stretching the earliest known cluster back to unimaginable times. However, it was expected that this would take some time because robustly identifying galaxy clusters typically necessitates the coexistence of two sets of observations. First, you'll need a wide-field photometric survey that can cover a large enough area to identify galaxy cluster candidates, galaxies whose colors are consistent with them all being very distant and at the same distance. There are three more surveys by the JWST that shed more light on the Big Bang: JADES, the JWST Advanced Deep Extragalactic Survey; GLASS, which examined the deeply lensed galaxy cluster Able 2744; and SEERS, the Cosmic Evolution Early Release Science Survey, have all already published their findings, with seers discovering 4 galaxies in the same narrow area of sky at the same distant redshift of 4.9, corresponding to a protocluster just 1.2 billion years after the Big Bang. However, within the glass field where the effects of a magnifying foreground galaxy cluster Abell 2744 are added, the potential for going even deeper abounds. And as luck would have it, and as far as we can tell it is truly just luck, 7 independent galaxies have been discovered in the same region and spectroscopically confirmed to be at the same redshift, 7.88, which corresponds to a time 650 million years after the Big Bang, the earliest protocluster of galaxies ever identified. The cluster's name, at least for the time being, is quite long, A2744Z7P90D, because it was discovered in the lensing field of Abell 2744 or A2744 at a redshift of 7.88, which rounds to 7.9, hence the Z7P9 part of the name, and its redshift was confirmed through the detection of doubly ionized oxygen in each of the 7-member galaxies, leaving it unclear whether the OD part is for the oxygen detection or because this protocluster represents an overdensity. The Hubble Space Telescope previously examined this galaxy cluster, which revealed over 130 times the average number of galaxies inside a fairly tiny region of space, which includes this newly detected protocluster. The most intriguing galaxy candidate from the Hubble research, however, was designated YD4, and it now turns out through spectroscopy to be a redshift of 8.38, indicating that it's not a member of this protocluster but rather a still more distant background object. This work not only reveals the most distant known protocluster or galaxies in the universe to date, but it also emphasizes how crucial it is to detect and spectroscopically validate all of the distant galaxy candidates that we anticipate will belong to a single entity. The previous Hubble analysis predicted a considerably larger, more expensive protocluster than exists. There are only roughly 24 times the number of galaxies in this cluster rather than the previously anticipated 130. Some of the galaxies discovered were not associated with the protocluster but rather were found elsewhere along the line of sight. Furthermore, some candidate galaxies still lack spectra, emphasizing the importance of observing them. The authors also attempted to quantify the mass and velocity dispersion, how fast galaxies move relative to one another within this protocluster, and discovered something remarkable. The aggregate mass of the 7-member galaxies is approximately 400 million suns, which is nearly the mass of the present Milky Way and therefore places a lower limit on the mass of the protocluster. It should have expanded to at least 5,000 times that size by now, or to the mass of the modern-day Coma cluster. And while the estimated velocity dispersion of 1,100 kilometers per second is highly uncertain, it appears to be remarkably consistent with known high-mass galaxy clusters. Now, the JWST again shocked scientists when it discovered a tiny early galaxy packing a big star-forming punch. The reason was that with the galaxy dating back to about 500 million years after the Big Bang, the galaxy could be a key to understanding how the cosmic dark ages came to an end. The galaxy known as RX J2129Z95 may be viewed at a redshift of 9.51. That number, which refers to the extent to which the light of the galaxy has been stretched by the expansion of the universe, indicates that we are seeing it as it existed only 510 million years after the Big Bang. RX J2129Z95 is extremely faint due to its great distance. However, the gravitational lensing effect of a massive foreground galaxy cluster called RX J2129.6+0005, which is located about 2.5 billion light-years from Earth along the same line of sight, boosted its light. The gravity of the 150 trillion solar mass cluster magnified and split the light of RX J2129Z95 into 3 pictures. JWST's near-spec instrument confirmed the galaxy's redshift, as well as strong emission from hydrogen and oxygen gas clouds within RX J2129Z95. And some of this galaxy's exceptional features have been revealed by these emission lines in the galaxy's spectrum. However, RX J2129Z95 is only 105.6 light-years across compared to our Milky Way galaxy's 100,000 light-year diameter, or even current dwarf galaxies that span several thousand light-years. And yet, despite having 1,000 times less the volume of the Milky Way, RX J2129Z95 has the same rate of star formation as our galaxy, implying that it is much more intense. The JWST is discovering that such high star formation rates are a pretty common feature of galaxies in the early universe. Although RX J2129Z95 is out of the ordinary, even for high redshift galaxies. The star formation rate is similar to other high redshift galaxies confirmed with NIRSpec, but the radius of the galaxy is at least 3 times smaller than those of other galaxies. This means a ton of star formation is compressed into a very small volume. The fact that all of these early galaxies are small despite their tremendous luminosity supports the prevalent hypothesis of hierarchical galaxy formation, which predicts that small galaxies form initially, then merge and develop into larger galaxies like the Milky Way. In addition, the team discovered no indication of an active supermassive black hole at the center of RX J2129Z95. This could be significant since this galaxy exists near the end of the cosmic dark ages when radiation ionized much of the universe's huge ocean of neutral hydrogen gas. One of the most pressing mysteries in cosmology has been what caused the end of the dark ages. Was it radiation from hungrily developing black holes or enormous bursts of star formation? If RX J2129Z95 is common, the lack of an evident black hole could indicate radiation from plentiful, bright young stars is the primary force in bringing the Dark Ages to an end. However, the amount of ionizing radiation produced by RX J2129Z95 has yet to be quantified. If there is a substantial population of similar galaxies, then perhaps they play a key role in the ionizing photon budget, speculated one astronomer. So more observations of galaxies at similar redshifts are needed, but with the JWST already confirming a handful of very high redshift luminous galaxies and much more likely to follow, astronomers will soon have a large sample to draw from. Another shocking discovery made by the JWST includes 6 galaxies that are too massive for their sizes. The Space Observatory discovered 6 huge galaxies that existed between 500 million and 700 million years after the universe's Big Bang. According to a new study, the revelation is fundamentally upending previous beliefs about the birth of galaxies. In a statement, research co-author Joel Leyer, assistant professor of astronomy and astrophysics at Penn State University, said these objects are way more massive than anyone expected. At this point in time, they expected to find only tiny young baby galaxies, but they discovered galaxies as mature as our own in what was previously thought to be the dawn of the universe. The James Webb Telescope views the universe in infrared light, which the human eye cannot see and is capable of detecting dim light from ancient stars and galaxies. The observatory can literally see back in time up to around 13.5 billion years by peering into the distant universe. This discovery that massive galaxy formation occurred extremely early in the history of the universe challenges what many astronomers thought was settled science. Due to this, they have jokingly dubbed these objects universe breakers. The galaxies are so huge that they contradict 99% of models of early galaxies in the universe, implying that scientists must reconsider how galaxies begin and evolve. According to current understanding, galaxies originated as tiny clouds of stars and dust that developed throughout time. Leia explained that they looked into the very early universe for the first time and they had no idea what they were going to find, but it turned out that they discovered something so unexpected that it actually causes problems for science because it calls into question the entire picture of early galaxy formation. When the Webb data and the telescope's first high-resolution images were released, Leigh and his colleagues began analyzing them. The galaxies showed as enormous points of light, and the team was astonished to see them, so surprised in fact that they assumed they had interpreted the data incorrectly. However, upon getting the data, they began modeling and attempting to figure out what they were because they were so large and bright. The first assumption was that they had made a mistake and would just discover it and move on with their lives. However, despite their best efforts, they have yet to discover that error. Now, taking a spectrum photograph of the galaxies, which includes splitting light into multiple wavelengths to identify various elements and estimate the true distance of the galaxies, is one technique to understand why the galaxies developed so swiftly. The data from spectroscopy would provide a more thorough look at the galaxies and their enormous size. A spectrum will tell scientists right away whether or not these things are real. It will explain how big they are and how far away they are. It's also feasible that the galaxies detected with the JWST's data are something totally else. Leia said that this is their first look back this far, so it's critical that they keep an open mind about what they see. While the data suggests they are most likely galaxies, there is a real possibility that a few of these objects are obscured supermassive black holes. Regardless, though, the amount of mass discovered means that the known mass of stars at this time in our universe is up to 100 times greater than previously thought. Even if the sample is cut in half, this is still a remarkable change.